Hi everyone! Today we're going to answer this optimization word problem using calculus. So in this question, we have a farmer and he has 60 meters of fencing that he wants to use to build an enclosure for his animals. This enclosure has to be split into two sections, one square and one rectangular. And we want to figure out what dimensions will maximize the area of this enclosure. Now, whenever I face a word problem, I try to visualize it. So let's draw the enclosure. Let's start with the width of the enclosure. We can call that X. And notice we have three sides that we can label X. Now let's look at the square section of this enclosure. Because we know it's a square, we can say that the sides at the top and the bottom are of length x. Now looking at the rectangular section of this enclosure, we can say that the sides at the top and bottom are of length y. So now we have our diagram. The next step is to find an equation that will help us solve for the area of this enclosure. The area of this enclosure would just be its length times its width. Now the length of this enclosure is x plus y. That's the square section plus the rectangular section. And the width is just x. And so we can say that the area of this enclosure is x plus y times x. Now let's expand out these brackets, and that would get us an area of x squared plus xy. Now the problem with this equation is we have two unknown variables, x and y. We want to make it so our equation is only in terms of x. So we need to find a way to write y in terms of x. In order to do this, we will need to find the perimeter of the enclosure. Perimeter is just the sum of all of the sides. So we can say we have 5 sides of length x, and we have 2 sides of length y. So our perimeter is equal to 5x plus 2y. And now what's really important for you to recognize is that we were given the perimeter. When we were told that the farmer has 60 meters of fencing, that 60 meters represents the perimeter because it's all of the material that will be used to make each side. So we can replace P with 60, and now we're going to isolate for y. And when we do that, we get y is equal to 30 minus 5 over 2x. So now we have y in terms of x. Looking back at our original area equation, we are going to replace y with the equation we just calculated using the perimeter. And when we do that, we get an area of x squared plus 30x minus 5 over 2x squared. Let's quickly simplify this to give us an area equation of negative 3 over 2x squared plus 30x. Now, before we move on, I want to make sure that you understand what this equation represents. This equation is a quadratic equation, which means if I draw an x and y plane, and notice instead of writing y, I wrote a to represent our area, I can plot this equation and it will give me a parabola, just like this. Now we were asked to find the maximum area for this enclosure. Looking at this parabola, I hope you can see that the maximum point would occur right here at the vertex. Now thinking about derivatives and tangent lines, what is the slope of the tangent line at the maximum? Well, the tangent line at the maximum would be a horizontal line. So it would have a slope of 0. And that's the key to answering this optimization problem. We have an equation for our area. We are going to find the derivative for that equation, and that will give us an equation for the slope of the tangent line. We will set that derivative equal to 0, and we will solve for our variable x. And that will help us find the width that will maximize the area of this enclosure. So let's do that. Looking at our area equation, we are going to find the derivative of this quadratic. In order to do this, you will need to use the power rule. And when you do that, you should find that the derivative of our area is negative 3x plus 30. This equation represents the slope of the tangent line. And we know that the slope of the tangent line is equal to 0 when it's at the maximum. So let's replace a prime with 0. And now all you need to do is solve for x. And when you do the math, you should see that x is equal to 10 meters. And what this means is that if the width of our enclosure and the length of that first square section is equal to 10 meters, it will maximize the area. But what about the other variable, y? We need to solve for that dimension. Well, luckily, we already have an equation for y in terms of x. So we have y is equal to 30 minus 5 over 2x. And all you need to do is plug our x value into that equation. And that gets us a y value of 5 meters. And really, that's the end of our question. We know that the width of the enclosure has to be 10 meters and the total length has to be 15 meters in order to maximize the area of this enclosure. And that would give us a maximum area of 150 meters squared. And now I actually want to prove this to you. So let's take the equation that we found for the area. So a is equal to negative 3 over 2x squared plus 30x. And let's plug this into a graphing calculator. You can see that I'm using Desmos. And when we plot this in Desmos, we get this quadratic. And I want to hone in on the maximum point, so the vertex of this quadratic. And I hope you can see that the maximum point occurs when we have a width of 10 meters and a total area of 150 meters squared. And really, that's the end of this question. But before you go, I really want to get your brains thinking about a few different ways that we could have answered this question. We approached this optimization problem using calculus, which I thought was a great method. But you didn't have to use calculus. Think about it. If we have this quadratic equation, which represents the area of the enclosure, we could have converted this quadratic, which is in standard form, into vertex form. And then we could have found the vertex, and that would have represented the maximum area. And there's another method we could have used. We could have taken this quadratic equation and we could have solved for our roots, so our x-intercepts. Then we could have taken the average of the x-intercepts, and this would have given us the axis of symmetry. The axis of symmetry occurs at the maximum point. So we could have used that to find the maximum area. Isn't it cool how many different ways we could have approached this problem? And I swear there's so many more out there. So please let me know in the comments if you have a different way of finding the maximum area. And with that, that's the end of this video. Thanks for watching, and I hope you have a great rest of your day. See ya!